Okay, as I said in the last video, I wanted to go over a couple of the solutions to the Lesson 6 problem set. So if you are watching this video, that means you have already completed the Lesson 6 problem set. If you have not, then go ahead and pause this and go back and work on those problems first. Okay, let's get started. All right, so the first problem has to do with these vacation photos that were initially sent to 7 people. And so we've got, the first number of people to view the photo was 7. But each of them sends it on to 5 of their friends, and so on. And we want to know how many people saw the photo, and we want our answer expressed in exponential notation. All right, so let's, I kind of breezed over that because you've already read it. But so let's look at, so the total number of people to view the photo in the first round is just the initial 7 people who saw it. Then after that, those 7 people send it on to 5. So we've got 5 times 7 people viewing the photo. So our total now is the 7 plus the 5 times 7. And I could write that as 7 plus 35, and then I could say that that's 42, but that's not going to help me express my answer in exponential notation, which is what I want to do. So we'll keep going. Okay, so 7 plus 5 times 7. Now, if you did do that addition, then it made it hard to see the structure of this expression, but let's keep going. So in the next round, we've got 5 times the 5 times 7. So the number of new people who saw it here was that. They sent it on to 5 of their friends each. So that's 5 times, really 5 times 35 here, right? Or 5 times 5 times 7. And that's what we added to the expression right over here. The 5 squared times 7. The 5 times 5. All right, so then in the next level, we had these people, these 5 times 5 times 7, they all sent it on to 5 of their friends. So now it's 5 times 5 times 5 times 7. So there's our 5 to the 3rd power of 5 cubed, and that's this part that we added to the expression right over here. So this part all stayed the same from this step. Okay, so we've got this expression. We have expressed it with exponents, so we could say we've put it in exponential notation. But we can write this expression in a simpler way, and that's where using the distributive property comes in. And so we want to, first, let's look at what the terms of this expression are. And so the parentheses help us to see the pieces that are being added together. And we could actually put parentheses around the 7 too, just to say that's one of the things that's being added here too. So all those things are being added together, and when we look at an expression like that, one of the things we're looking for is a common factor in every term. And we have a common factor here, and the common factor is 7. Every one of these terms in this expression has a 7. And so we can factor out the 7. So what we're going to do is we're going to take out that 7 as a factor from each of those terms, and then we have to think about what we would multiply it by to get it back. And so the reason I'm spending time on this too, just so you know now, is being able to do this is going to really help you in algebra as you move along in your math career, not just this year, but years down the road, to be able to work with expressions this way. So let's see what we get. So what we need to do is think about, well, what do I need to multiply 7 by to get this first term, 7? Well, that's pretty easy. I just need a 1, right? 7 times 1 would give me this term back out. Well, 7 times what would give me this term now? Now I'm looking at the second term. Well, we can see that it's just multiplied by 5. So 5 would give us that, and now 7, oops, didn't mean to do that. 7 times what over here is going to give me this term? Well, that would just be the 5 squared and then the 5 cubed. Okay, so then we have our expression here. So if I took and distributed this 7 through here, then I would have this expression. But you can see this is so much easier to read. We can see what's happening with these terms now, whereas here it was a little crowded. So just by taking that 7 out, made this look so much clearer. But there's one more thing we can do. This 1 looks a little funny here. It looks like it doesn't belong, right? Why is this 1 here with all these 5s? Well, one thing that we can do, and what your answer key did, is to think, can I write 1 with a base of 5? Can I change the base? Can I write this value of 1, can I write it as a power of 5? So think about that. Okay, so turns out we can, right? So we can have 7 times, we can replace the 1 with 5 to the 0. And if we're going to do that, maybe we want to show the exponent on the 5 term as well. And we still have 5 squared, 5 cubed. So there's another way we could write this expression. There's nothing wrong with this one. But this one shows that progression of the exponents on the base of 5, from 0 to 1 to 2 to 3. Okay, so both of these expressions are definitely simpler than this one. Okay, so I hope you maybe see the value more of the distributive property, and also the relationship to that previous problem. So that's what I want to do now, is I want to look at the ball drop problem. So back in lesson 2, problem number 1 of your problem set was this ball drop problem where a ball was dropped from 10 feet and then it bounced back up 2/3 of the way on each bounce. So it went down 10 feet and then up 2/3 of 10, back down 2/3 of 10, and then back up 2/3 of this distance and back down, and then once again 2/3 of this distance. So you can see the 2/3 times 2/3 times 2/3 coming up in this expression. So we've got the initial 10 feet, that drop, and then we're going to add to that this distance here, and so that looks like that. So it's 2 for the up and down times 2/3 of 10, okay? And then the next term we add is plus 2 times 2/3 times 2/3 of 10. So that gives us the 2/3 squared, and then we could even go one more, I think I have on here. Yeah, so 2/3 of 2/3 of 2/3 of 10. So you get the 2/3 cubed. And so you can see these repeated factors in each of these terms. So what are those repeated factors? Okay, so we can see that each of the terms that have the 2/3 in them each have a 2 and a 10. A factor of 2 and 10 are in each of those terms. And so we can rewrite this expression. So I still have my initial 10-foot drop. I'm just going to always carry that along. But then each of these, the 2 times the 10, I can write as 20, right? So each of these has a factor of 20 in it. So I'm going to take that 20 out and then think about what's left in the parentheses. Well, if I take the 2 and the 10 out here, the only thing left is the 2/3 right here. So I've got the 2/3 plus, and then in this term, I've got the 2 times the 10 and the 2/3 squared. So I've got 2/3 squared and 2/3 cubed. Now, remember, this ball drop problem went to the 30th bounce and then to the nth bounce. But the basic structure of the expression is the same in any of those. So we've got this 20 times 2/3 times 2/3 to the second to the third. And so we can see the structure of what's going on here with the bouncing a lot better now. But we can even take it a step further, because we'll notice that within this parentheses, each of the terms here has a common factor. So we can even factor a little bit more, and this is what your answer key did, and it caused a little bit of confusion for some people. So let's look at what that would look like. First of all, what is that common factor? Pause and think about this. That is in each of these terms. Yeah, so the factor that we can see that in each of these terms there's at least one factor of 2/3. This one only has one, so that kind of limits us. These have more than one, but the first one only has one. But that means we can factor out a 2/3. So now notice the difference here. I've taken the 2/3 outside the parentheses, and so now we'll have different terms inside here to reflect that there's a 2/3 that's going to multiply everything in here. So let's look at what would go in that first spot now that I've taken 2/3 out. And so to get 2/3 times, whoops, that's not where I meant my pointer to be. 2/3 times what is going to give me this 2/3 back out? Well, it's the same thing we just saw, right? Go ahead and think about what number would go in that first place inside the parentheses here. Okay, so it should be a 1, right? Because now I've got the 20 times the 2/3 times 1 would give me this expression here, because this is just this one here. This term is 20 times 2/3, so that's that right there. So there's the 1, and then with each term that comes after it, we're going to notice that the exponent is lowered by 1. So instead of squared here, we have to the first power, and I can actually even put that in. This would be to the first power right there. And in the next term, it's going to be squared. And so we have an even simpler expression within the parentheses, but either of these would be either this one or this one would be really clearly written and show the structure of what's happening with the 2/3 factors in that ball drop problem. Okay, so I hope maybe that gives a little more explanation to some of you who were wondering, where does that 1 come from and why are we factoring it this way? Well, the whole reason is just to make it clearer to read. Okay, so for numbers 2 through 5, I'm just going to let you compare your answers to those in the teacher edition. They're very clearly written with good reasons given. I just want to kind of reiterate why we're doing this, okay? So what we want to do is use only the definitions of positive, negative, and zero exponents. We know these definitions that, a exponential expression the exponent tells me how many times to use the base as a factor and such things like that. The negative exponent is the reciprocal of the positive exponent, and zero exponents we found are equal to 1, and there's a good reason for that. And so we're only going to use those definitions and develop that the rules for exponents work for negative numbers. So we'll use the properties of exponents for positive integers, and those are numbers 1 through 8 on that equation reference chart that you were given in your notes, and develop that those properties actually work just the same for positive, negative, and zero integers. And so that's what we're doing there. And we're being really flexible with our exponents and getting used to using them in different ways. And so hopefully you have maybe been working on those sprints and getting a little quicker at how you think about when you add exponents, when you multiply them, when you subtract them, and so on. All right, so you can look at those on the answer key. So the last one I want to look at is number 7. And number 7 gave you this expression and said to use the properties of exponents to write an equivalent expression that is a product of distinct primes. All right, so what I want you to do now is tell me what does it mean to write something as a product of distinct primes? Okay, so in that we had 3 words. We had product and product, meaning things that are what you get when you multiply things together, okay? So the expression is going to be a product. That means it's going to be expressed as multiplication. And then it's going to be a product of distinct. So I'm going to write these 2 words, distinct. You know, and sometimes when you're reading a math problem and you don't know what the words mean or you don't know what they mean in the context, it's a good idea to look them up, okay? So product, we know what that means. Distinct just means separate or different, okay? We want them to be all different in our product. We don't want to have something repeated, the same one repeated multiple times. And we want them to be primes. So remember, prime numbers are numbers who have exactly 2 factors, and those 2 factors are 1 and itself, okay? So want to tell you something here. One thing that students might be tempted to do on this problem is to use a calculator. You don't want to do that, right? We don't want to multiply. I don't want to use a calculator to find 10 to the 5th times 9 squared divided by 6 to the 4th, because I've been told to express it as a product of distinct primes. The calculator's not going to help me do that. Furthermore, it just complicates things, so don't use a calculator. We're going to simplify this expression, okay? And you're going to find that it gets really simple, right? If you've done this problem, you saw that. So let's think about how I can take these numbers now. 10 and 9 and 6 are all what we call composite numbers. They're not primes because they have other factors. So I can express them as products of prime factors. So 10 can be expressed as 2 times 5. So I'm going to write that as 2 times 5 to the 5th. 9 can be written as 3 times 3. And I'll just put it here as 3 squared, and then that's still squared, right? So 9 is 3 times 3. 3 is a prime, 5 is a prime, 2 is a prime. And then 6 can be written as 2 times 3. So I'm going to write that as 2 times 3 to the 4th. And then I'm going to put my distinct primes in different colors. So I've got 2s and 5s. So I've taken this product and used that exponent rule that says if 2 things are being multiplied together, I can raise them separately to the power. So this is 2 to the 5th times 5 to the 5th. When I have a power to a power, I'm going to multiply. So 3 squared squared becomes 3 to the 4th. And then down on the bottom, I'm going to use that same rule again and write that as 2 to the 4th times 3 to the 4th. Okay, so now I have a product of primes. These are all prime numbers that I'm multiplying together, various numbers of them, right? But they're primes, but they're not distinct primes. So what I need to do is combine the ones that have bases that are the same. So this one, these are a base of 2, these are a base of 3, and a base of 5. So I can simplify this. And I'm going to write it as the product of 3 separate things. So I've got kind of this fraction here that's my base of 2, then I have this base of 5, and then I have the base of 3. And so now I can see how I can simplify that. That's 2 to the 5 minus 4. because I'm going to subtract my exponents when I divide. The 5 to the 5th just stays the same. And 3 to the 4th over 3 to the 4th is a fancy way, whoops, of saying 1, right? So this becomes my my factor of 1, which isn't going to change anything, so I can leave it off. So now I've got 2 to the 5 minus 4 times 5 to the 5th, which is just 2 to the 1st power, or 2 times 5 to the 5th. So I went from this expression up here down to this expression, which would be fairly simple to throw into a calculator if I wanted to, without a whole lot of effort. And this, of course, all these steps didn't need to be taken. Maybe you could have done it in a little bit less steps, but I can simplify it down like that. So product of distinct primes, and that's what we have here. It's 2's and 5's being multiplied together and written in an exponential way. All right, so that is what I wanted to go over for the lesson 6 problem set. So hopefully this is good preparation for you for the mid-module assessment. You might want to go back and just briefly review what we talked about in lessons 1 through 5 and in this problem set. And then take a stab at the mid-module assessment. Do your best. I mean, really give some good explanations that are being asked for, and look at those problems. I think you're well prepared, and you can go ahead and correct that on your own. And I'll have a little video that will help you review some of those problems if you need more explanation. If you don't, then you can go right on to lesson 7. And when we come back to class, I'd like to collect your mid-module assessments because I like to see those. So, all right, well, good luck, and we'll see you back here for lesson 7.